All right, everybody. Well, if you weren't able to be in class when we talked about the impulse momentum theorem and did our little demo, I want to make sure you can see it, okay? Because this is super valuable. This is amazing, actually. It's one of my favorite demos. So what I have here is I have a little cart, okay? And the cart has a bungee attached to it, okay? The bungee is attached to my force sensor right here, okay? So, boom, right here. Perfect. So over here, I've got my motion sensor. The motion sensor, remember, the way I've got it calibrated is as it goes in this direction, that is the negative direction. Negative, positive. So if it's going this way, it's going to have a negative velocity. If it comes back like this, positive velocity. Now I know you can't see the screen up here very well. So when I get the data, I'm going to show you what it looks like up here on the board. Okay. So I'm just going to give it a push like this. And here's the idea behind this. While this is slack like this, this thing should not be measuring any force. But as soon as it does this, whoa, now it starts to pull in this direction, okay? And what's going to happen is this thing's velocity is going to decrease, 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 0, and then come back. Now look, it goes slack again. This now should register 0 force again. So the idea is this. If I know how long this bungee, oh, that was good. If I know how long this bungee is actually pulling or has tension, that delta T, and I can see what this force graph looks like over time, if I can take the integral, okay, if I can add up all the little tiny areas, let's just make like little tiny rectangular areas underneath this graph, if I can add all of those up using calculus, thanks Newton, I can actually, that right there, that F delta T, that is my impulse. And impulse equals the change in velocity of this thing over time. All right, so I'm going to retie this really quickly. Sorry about this. I'm glad it happened before I gave it a nice hard push. All right, so there we go. I am going to click record, and then I'm going to come over and I'm going to give it a push. Okay, here we go. 3, 2, 1. Do it again. All right. Oh, beautiful. I can see we've got some great data. So here, I'm going to grab my phone, and I'm going to bring it over here. All right. Wow. Okay, so I hope you guys can see this. I've got this in my little stand. Hang on one second. I'm going to take this out. Okay. Oh, that's so beautiful. So here's what we have. On the top, that is my force time graph, okay? So this is force over time, all right? And that delta T right there, oh, I can see it, is actually 0.42. So 0.42 seconds. So that is the amount of time from here to here that force is being applied. Whoa! If I can actually figure out the area under this, thanks Newton, if I can do that using a little bit of calculus, this right here allows me to integrate or essentially add up all these little things in all these little tiny, tiny, tiny time periods, okay? So that right there, Newton had no idea we'd ever create software that can have a high school student do it like that, all right? So now this is so cool. This takes us back to our graph matching days, woo! This is a position time graph. This is our velocity time graph. Pretty cool. So if I wanted to find the velocity before the force started being applied, that's right here. Oh, get your head out of the way. That's right here, okay? And look, it's a negative slope. That means that it's heading towards the motion sensor, towards the motion sensor, okay? And this is a constant slope right here. So if I could find the slope, and we've done this many times using this software, if I can find the slope here, that is my initial velocity. And now look at this. For this short period right here, the thing is not changing its position. That means it's basically got 0 velocity right here. And now it comes back the other way right here, and now it's going away from the sensor at a constant velocity. I could also cheat a little bit, and I could use the velocity value right here and the velocity value right here. Remember, this is going to be your V final. It's positive minus a V initial, okay? I will say right here, which is a negative. So V final, positive something, minus a negative. Oh, I'm going to add up these velocities, and I'm going to multiply that times the mass of this thing. And this thing actually has a mass of 761 grams. 761 grams. So what I end up with is my mass times my V final minus V initial equals F delta T. All right? And that's how we solve this animal. All right, welcome back. Now, I know this is difficult to see, but here's what I've done. So I highlighted that top little thing right here, okay? And I clicked my little integrate icon right here, and it spit out a number of 1.57 Newton seconds. 1.57 Newton seconds. Well, guess what? That's a force times a delta T, okay? That's the impulse right there. Okay, so that's that part. Now this right here, this side of the equation is the delta P. Okay, I've got my mass right there, 0.761, so it's 761 grams. This right here was the final velocity. Remember, as it shot back that way, that was a positive velocity. So V final minus V initial. Well, the V initial was a negative 1.09. So if I do this math, 0.761 times 0.985 plus, right, because a minus of a minus, 0.985 plus 1.09, guess what I get? And I'm not even kidding. It's like 1.576, rounds up to about 1.58. This right here is what Newton's calculus provided me for an answer, all right? So this side of the equation is almost exactly identical to this, using a contraption that consists of masking tape and duct tape and cardboard, and you get it. All right? So this stuff works. Impulse equals the change in momentum, and it's absolutely beautiful. Hope you guys enjoyed it.